Hi, my name is Sky Nelson Isaacs. I'm a physicist with a master's in physics from San Francisco State University, and I'm going to talk today about the new physics of the matrix. The world is a holographic simulation. I have an organization I began called the Synchronicity Institute. And I didn't start off researching the matrix or holographic simulation or any of those very sort of out there topics. I started off many, many years ago in college being interested in some basic ideas around the Fourier transform and holograms. I created a hologram in college and just was mesmerized by the experience. And so after I graduated from a master's program, I was able to get funding from the generous Federico and Elvia Faggin Foundation and pursue this line of research officially. So that's what you're going to see the results of today. I want to start off, we're going to get into some real physics, but I wanted to start off with setting the stage. Why are we talking about the matrix? In the Matrix, we have a virtual world. This is a movie about a virtual world that appears very real. And what is it that makes the virtual world interesting? It's the fact that it is adjustable, that history in the Matrix is adjustable. The timelines of things are adjustable. What do I mean by that? Well, the whole point of the movie is essentially Neo, the hero, battling Agent Smith. And Agent Smith is, in the Matrix, he's an NPC or a non-player character, meaning he's kind of like a robot in the game. And the whole point of the movie is that they meet each other, right? They do battle. So in order for them to do battle, they have to be programmed to somehow find each other in a building, let's say. Let's say Neo goes into this building and he has a choice of going right or left. How do we know he's going to pick a direction where he actually meets Agent Smith? And therefore the plot unfolds. Because if he doesn't meet Agent Smith, the plot doesn't unfold. So in movies generally rely on this idea of synchronicity quite a lot. And I'm going to explain how that can work in a technical perspective. So if Neo decides to go straight, Agent Smith here is described as a branching tree of different timelines, and that timeline can become the one that actually is. There's a retroactive adjustment. We're saying the timeline of Agent Smith is flexible to the choices that Neo makes. If Neo decides to go to the right, that other branch can come true. So we're talking about timelines that must be described as a whole. We're going to talk today about the idea of time slicing, and this is something that's done in physics really from the beginning, from classical mechanics through quantum mechanics through today. We slice up time into steps, into moments. And if we do that, then there's no real way to say, you know, I can just reverse time. But if time as a whole is a whole branch going from the past to some point in the future, then if it's described and defined as a whole, then you can roll it back in a sense more readily and go to a different branch. So that's why we're talking about, we're going to talk about branches as a whole, time as a whole. So the central point is as a whole timelines. If timelines are defined as a whole, not moment by moment, then they can be retroactively adjusted and give us essentially the matrix. This is called retroactive event determination in my papers. So the history of research into time, there's a lot of it. So we're going to focus mostly on time slicing today. I'm not going to go into this slide, but you can pause it if you'd like. The motivation for the connection between a new formulation that's in some sense treats time differently than the one that we currently have in quantum mechanics and quantum field theory is the fact that Richard Feynman, in his path integral formulation of quantum mechanics, makes an assumption about time. The same assumption I just said, that time is sliced. Because he defines a path as a sequence of configurations over successive times. Now, if you know about the path integral, then you realize that what it says is to go from point x0 to point xt, the particle can go over any possible path, not just in a straight line, but any available path. And then those paths are added together and an amplitude is found and a probability is found for the most likely path, or actually the likelihood of that transition happening. So what isn't talked about is that this is always in a straight line through time. We're slicing up time into moments. If time was treated the same as space in this formalism, then you could go over all possible times as well, but that's not how it works. We always impose this sequence of configurations for successive times. And at each of these slices, we do what people do in physics all the time. We insert a complete x, which is position, and k, which is momentum basis at each moment. In other words, we're inserting these integrals over position and momentum at each time that we slice this progress. And that is essentially assumption of a privileged present now moment. So we may not even realize it when we do the path integral theory, but we're assuming what I call a metaphysical assumption, that there's a privileged present now moment. We're going to drop that assumption. So let's talk for a minute about holograms. When you shine light on an object like the city here, and then you capture that light on a film with reference light coming off a mirror, you capture the light as a whole, and you get a hologram, which looks something like this. This really cool video of a city hologram. Looks very realistic. And you can see the buildings have parallax, meaning they move past each other. But the bottom line is this is not an actual three-dimensional model. It's just light patterns coming off of the film and tricking your eyes. Because when you tilt it up, you see there's nothing there. And tilt it that way is just a blank piece of film. Or not blank, but it's got interference patterns on it. So how does that work? We need to talk about the frequency domain. This is the essence of how we get to as a whole timelines. The frequency domain is a dual space to regular space. So in regular space on the left, we have a pattern. And that pattern is vertically spaced lines and pretty high frequency, pretty rapidly alternating. And so in the frequency domain, that's a dot above the central axis, a pretty far distance up, and another dot to the bottom as well. And that represents a single frequency in the right direction at the right frequency. Now, that's a lot of information, or it seems like a lot of information on the left, but on the right, you see that's really just 2 points of information, very basic information. So the frequency domain captures information about patterns. And here we have a pattern going from left to right, and it's lower frequency, greater spacing. So there's a lower frequency, a lower distance to the origin in the frequency domain. And you can do this at an angle as well and put the dots at an angle. So the frequency domain is describing what patterns are present in the physical space. So now we can do this in an even cooler way. We can take a city image like this and ask, what happens if we break this down into straight lines, into patterns of straight lines, which are called plane waves? Well, if you can actually break this down into a very complex recipe of straight line patterns that is given in the picture below, where you've got a dot for every possible orientation and every possible frequency of line. And I'm going to prove to you that this recipe on the bottom gives you the city on the top. So the city here is on the left, and I'm just going to add lines one at a time from that recipe. And it looks like a mishmash of hashed lines, but gradually you start to see with enough detail, enough frequencies present, you get to see the actual city emerge. It's pretty amazing. You can actually do that with a low pass filter too. I'm going to start the filter here on the left and just include the very smallest frequencies, and then outward it can include more and more high detail frequencies. And what that looks like on the right, when you add those in the right order, the low frequencies first, watch carefully, it's going to happen fast. Okay, it goes from being very blurry right away to quickly filling in the details. So early on, with just those low frequencies, it was pretty blurry, just the basic design. And then as we added frequencies, we added detail, added higher frequencies. And here we've got most of the pattern in place, but there's still some artifacts due to some of the higher frequencies not being present yet. So let's look at those artifacts. Here again is our city and the recipe of frequency space that made it. And here's that frequency domain with a couple of masks put on it. So these are just blacked out regions that we've removed some of the frequencies. We've removed some of the low frequencies, which are the most important for overall slow varying patterns. And you can see that we've introduced some artifacts, some wavy lines where there really shouldn't be wavy lines. That's because we've removed some necessary information. Now the key point here, this is the key point of really the whole presentation, is that by changing the one little region of the frequency domain, we've altered the entire space-time or spatial city structure. This one change in a local region of the picture up here has changed the entire, made artifacts over the entire picture down here. So in order to make use of that fact, I'm going to compare quantum mechanics to optical image propagation. We're going to try to use the mechanics of optics and make it equivalent to quantum mechanics, and then use that to ask ourselves, what would time be like if we didn't time slice? So quantum mechanics is like optical image propagation. You start with a plane wave coming in, illuminating the film. And this film is just like a picture of something, or an acetate with something on it, Fa. And from that you get a waveform, GT. And that propagates with the impulse response, that's H, and lands on a screen with the final waveform, GF. The same exact mathematics applies to the wave function, where you start with psi I, and then you have an x-dependent Hamiltonian, which is essentially the potential, which creates your image. And then you have some psi t, which is the transmitted waveform. And then you have a propagation factor, which is the Hamiltonian's free particle propagator. And then you have the final waveform. And the measurement of the final waveform is kind of like landing on a screen and viewing the image that we had up here. So here's the formalism. There's two postulates. One, the wave function is four-dimensional, just like space-time. Now let me explain what I mean. A normal wave function in quantum mechanics is three-dimensional, and it has an external parameter of time. So at any time you can say it's 5:10. I'm going to check the wave function, and you can do that, and it makes sense. It's spread over space, and you can calculate probability of where everything is in space. That means x, the position of the wave function, is varying as a function of time, and that's what we've done in quantum mechanics and classical mechanics for the last few hundred years. How do we not treat time as the central clock, as the central guiding independent parameter? We can't. So we can use this idea that wave function propagation in quantum mechanics is just like optics. And we can say, okay, optics we understand, signal propagation we understand. We use that in industry all the time. And we know how to do a Fourier transform, for instance, of a sound file and transform it into the frequency domain. That's time, right? Time-based variation. So now we're going to treat the four dimensions of space-time as simply a signal in space-time and do a four-dimensional Fourier transform to just like we would in signal processing. And now time is no longer an external parameter. Time is one of the dimensions, and nothing is varying with respect to time. We don't have an extra clock that's ticking on the outside. So we can't slice this entity, this four-dimensional wave function. We can't slice it at a certain time and get anything meaningful. It's actually more like a hologram in which encodes the motion that's allowed. Okay, so it doesn't actually describe directly a picture of space. It encodes the motions that are allowed, the equation of motion. And so interactions, then postulate 2 is that interactions are convolution. The wave function is essentially a convolution of the original wave function with some potential function here, f, and convolved with a impulse response function. And due to the convolution theorem in mathematics, this is essentially taking the Fourier transforms of the initial signal and the impulse response, multiplying them together in frequency space, and then inverse transforming them back into regular space. So this is really interesting. It's really simple. It's really symmetric and appealing, because what we're doing is saying the way we do interactions in the world is we start in regular space, we convert to the frequency domain, we interact them, and then we convert back to regular space. That's a nice description of dynamics. So I'm going to show that this reduces to the Feynman path integral. The main observation is that the weight of a path in Dirac's language is e to the I s, where s is the action, usually written as a time integral of Lagrangian. But this same formalism can also be written as a series of recursive forward and inverse Fourier transform pairs. And so we start with e to the I s, we write it as an integral over t of the Lagrangian. And then we write the Lagrangian in this Legendre transform, which is p, the momentum, times x dot, which is the velocity, minus the Hamiltonian h. But then we break it out step by step, and we say that this is a Riemann sum instead of an integral, so it's a bunch of bitwise sums. And the momentum times the velocity, well, the velocity is a change in position, so that's why I've got this index position here, divided by a time step. So now we're slicing time here. We've got this time step tau, and that's minus h times this factor of tau that pops out here. Now, if you just jump to the bottom line, you'll see that this turns into a series of factors. A Fourier transform kernel here, e to the I minus IPX, and that's a forward Fourier transform kernel. This is an inverse Fourier transform kernel. And this is the time evolution operator. So now that first thing there is going to do a Fourier transform, and the second thing there is going to do an inverse Fourier transform. So in real life, all of this happens inside of an integral, and it looks like this. we have the wave function having a Fourier transform with that kernel and this integral, and then an inverse Fourier transform with that kernel and this integral. And then that happens again, so that we're doing 2 time steps here in this example, just to be explicit. And it can also be shown, you know, so far we've only done it over position and momentum, but we want to be symmetric with time. And so time and energy have a similar relationship here. And if we do the same process here with time and energy, we get just what we expect for the time evolution of a stationary state, e to the I times the energy times the time step. So all of this brings us to a very direct connection between the Feynman path integral in the case of time slicing and a recursive set of Fourier transform, inverse Fourier transform steps. And this is a little complex of a screen, but the blue here represents or shows you one Fourier transform and inverse Fourier transform with these extra phase factors in there. Notice that the phase factors are essentially can be reduced to the Schrodinger equation. The Schrodinger equation is based on the information that makes the wave function evolve is the momentum dependence of the Hamiltonian and the position dependence of the Hamiltonian. And both of those show up in these phase factors here in certain places. So we've got one time step here in blue, and the next time step here is another forward and inverse Fourier transform pair. And that works out to be just what you find in the standard textbook for the path integral. Now, last thing we're going to talk about is parameters and coordinate intervals. This is a very crucial thing that pops out of this. Parameters are these, what we call unmeasurable things, and coordinate intervals are measurable. It turns out there are 2 distinct measures of time and space in this theory, just like a hologram. Now, hologram, you look at a hologram and you see the image of the city, but you don't really notice that there's a background. There's a film there. So the parameters describe the film itself, the waveforms on the film. But the buildings are described by what you can measure, the coordinate intervals. So I'm going to place a triangle in the very center of this film, and I'm going to tilt the film, and the triangle is going to stay in place. But you'll see what the buildings are behind it is going to change. So the building right there now behind it is now no longer behind it in the same way. And now a different building is behind the triangle. So there's a coordinate that describes the buildings, and there's a parameter that describes the layout of the film itself. We've decoupled these 2 things. This is like Plato's allegory of the cave, where on the wall you have a projection. That's what you can see. That's the coordinate intervals. But behind you is something that's projecting that you can't see. You don't know what the source is. All you see is a projection. So there's a corollary to this that pops out of this theory based on, that relates to Wheeler's delayed choice experiment. And Wheeler's delayed choice experiment is an experiment that I won't go into, but it shows that a choice at the end of an experiment can affect the path that must have been taken by the particle in the process of the experiment. This shows up very naturally here because the 4D frequency domain cannot change in time. It doesn't have an external time parameter. It is a distribution over space and time. And so it corresponds to an alternate outcome. Every version of the 4D frequency domain in space and time corresponds to a different, unique, entire path. Because if you change the path, for instance, if I put a detector in the middle of this path, I've suddenly changed the endpoint of the light traveling, and that corresponds to a different outcome, corresponds to a different distance of travel. And that means that the entire recipe for the motion has changed. You change the endpoint of the travel, you change the entire recipe for the motion in the frequency domain. So there's more to go into about that I don't have time for, but essentially each of these is a recipe for one particular type of travel, and the travel is defined as a whole. It's a big jump to take these conclusions to the macroscopic world, but I do make that argument in my paper. So to take us back to matrix and timelines are flexible argument, Neo walks into the building, he goes and finds Agent Smith, but if he makes a different choice and goes down a different pathway, he finds Agent Smith there too. So there's some experimental data that supports, or is consistent with, I should say, this model, the relational model of quantum mechanics and Wigner's friend paradox, as well as measuring momentum space representation, measuring holograms of a single photon. These are some of the experimental results that could be beneficial to testing this. And I'd like to have you reach out to me if you'd like to read the paper. I have a book out called Leap to Wholeness, How the World is Programmed to Help Us Grow, Heal, and Adapt. And some references for you to check out. Thanks a lot for tuning in, and I hope you have a great conference. And thanks to Abby and the team for holding all of this space for us. I really appreciate it.